Ever stop to think about the unseen pushes and pulls, the forces acting on us every day that we just sort of take for granted?
That's true. They're everywhere.
Well, today we're doing a deep dive into one of those really fundamental, fascinating concepts, pressure, specifically pressure in fluids and, in the atmosphere.
And we've got some great listener-provided material to work with here.
Yeah, a really good mix. We've got syllabi points, core definitions, some great examples, experiments, applications. It's quite comprehensive.
Absolutely. Looks like a solid base to really get into the nuts and bolts of pressure.
So our mission, as always, is to sift through this, pull out the crucial insights, and, well, make it all clear and hopefully pretty engaging.
Let's do it. Where should we start?
Let's begin right at the basics. Thrust and pressure. So thrust, fundamentally, it's a force, right? Acting perpendicularly or normally onto a surface.
Right. And it's a vector quantity. It has direction, measured in newtons in the SI system.
Exactly.
Yeah.
And pressure then takes that thrust, that force, and relates it to the area it's spread over. So thrust per unit area.
Which makes it a scalar quantity. Just magnitude. No direction needed for pressure itself. And the SI unit is the Pascal, or Newton per square meter.
Okay, think about standing on, say, soft sand versus lying down on it.
Good example. Your weight, the thrust downwards, is the same in both cases.
But when you stand, all that force is on the small area of your feet. High pressure, right? You sink in.
But lie down, and you spread that same weight over a much bigger area. The pressure drops way down, and you stay on top.
It perfectly shows that inverse relationship. Same force, bigger area means lower pressure.
Exactly. And it highlights how crucial area is.
Now, you mentioned pascals, but there are quite a few units for pressure floating around, aren't there?
Oh, definitely. Besides the Pascal, you've got kgf per square meter, dyne per square centimeter in the old CGS system, then bar, millibar, the atmosphere, or atm.
Padium, often used with barometers, right? Millimeters of mercury.
That's the one. And knowing the conversions is useful. Like a bar is 100,000 pascals, 105. Standard atmospheric pressure is roughly 1 at 8m, which is about 101,325 pascals, or 760 torr.
So it seems the context often dictates the unit used.
Pretty much. Meteorology often uses millibars. Vacuum systems might use torr or pascals.
Okay, so the key factors affecting pressure are, well, obviously the thrust.
And the area it acts on. It's those two.
Let's use that brick example again. A single brick has a constant weight, a constant thrust.
Right. Place it on its smallest end face. The area is small.
So the pressure underneath is high.
Exactly. Now lay it flat on its widest side. Same thrust, much larger area.
Much lower pressure. Makes sense.
And the other way around. Keep the area constant, keep the brick flat, but stack another brick on top.
Now you've increased the thrust, the total weight.
So the pressure increases. Direct relationship between thrust and pressure, inverse between area and pressure.
And understanding this lets us, well, manipulate pressure deliberately.
Absolutely. If you want high pressure, like for cutting or piercing.
You make the area tiny. Think of a nail's point or knife edge. Concentrates the force.
And if you want low pressure, to avoid sinking or damaging a surface.
You increase the area, like wide railway sleepers under the tracks or the broad foundations of buildings, spreads the load.
Precisely. It's about distributing that force effectively.
Okay, that covers solids pretty well. Let's transition now to fluids. How does pressure work there? It feels a bit different.
It is different in some key ways. First, what's a fluid? Basically anything that can flow so. Liquids and gases.
Right. Not rigid like a solid.
And because they flow and they have weight, fluids exert pressure. But unlike a solid just pressing down, fluids press outwards too. In all directions, actually.
All directions. How does that work?
It's due to the weight of the fluid column above any point, combined with the fact that the particles are mobile and constantly colliding with each other and the container walls.
Ah, okay. Is there a way to sort of see this?
There's a classic demonstration. Imagine a tall vessel, like a cylinder, filled with water, and it has small holes drilled in the side at different heights.
Okay, I can picture that.
If you unblock those holes, what happens?
Well, water would spurt out, right?
Exactly. Water comes out of all the holes, showing there's pressure at every depth, but there's more.
Let me guess. The water from the lower holes shoots out further.
Precisely. The jet from the deepest hole travels the farthest horizontally before hitting the ground. The one from the shallowest hole lands closest.
So that visually demonstrates that the pressure increases the deeper you go.
It's a direct consequence of the weight of the water column above that point. More water above means more weight, hence more pressure.
And this leads to a specific formula, doesn't it? P equals HROG.
That's the one. P equals egg state grade. Let's break it down. P is the pressure due to the liquid itself at a certain point.
P is the depth of that point below the surface of the liquid.
Correct. That's the Greek letter rho. Stands for the density of the liquid, how much mass per unit volume. Denser liquids exert more pressure at the same depth.
And G is the acceleration due to gravity, which pulls the liquid down, creating the weight.
Exactly. So pressure depends directly on depth, density, and gravity.
But that's just the pressure from the liquid itself. What if the container is open to the air?
Good point. Then you have atmospheric pressure, let's call it P, pushing down on the surface.
So the total pressure at depth would be?
The sum of both.
Right.
Total equals P plus egg, atmospheric pressure plus the liquid pressure.
What's interesting is what pressure in a liquid doesn't depend on.
Right. It's independent of the shape of the container. A narrow vase or a wide tank, at the same depth, the pressure is the same, assuming the same liquid.
And it also doesn't depend on the area of the surface we're considering at that depth. Pressure is pressure at a point.
Correct. Depth, density, gravity. Those are the key factors for pressure within the liquid itself.
So, based on this, we can state some fundamental laws about liquid pressure.
We can. First, as we've seen, pressure increases with depth.
Second, in a stationary liquid, pressure is the same at all points on the same horizontal level.
Yep. Third, pressure at any point within the liquid acts equally in all directions, up, down, sideways.
Fourth, at the same depth, pressure varies with the liquid's density. Denser liquid, higher pressure.
Like comparing oil and water, perhaps. And finally, the principle that the liquid seeks its own level. If you have interconnected containers, the liquid surface will be at the same height in all of them, regardless of their shape.
That last one explains those self-leveling water gauges you sometimes see.
Exactly. And these laws have some really significant consequences in the real world.
Like, you mentioned density. Seawater is denser than river water, right?
It is because of the dissolved salts. So at the same depth, say 10 meters down, the pressure in the sea is noticeably higher than in a freshwater lake.
Okay. And what about engineering? Dams, for instance.
Dams have to withstand enormous pressure, especially near the bottom, where the depth is greatest. That's why they're always built much, much thicker at the base than at the top, to handle that P equals high increase.
Makes sense. And water towers in towns, they're always placed up high.
That's also about pressure. Placing the tank high up creates sufficient head, or height, HHH, to ensure adequate water pressure in the pipes and taps down below. Gravity does the work.
Right. And deep sea divers?
Yeah.
The pressure down there must be immense.
Absolutely. Way beyond normal atmospheric pressure. It can easily exceed the pressure of the blood in our bodies. That's why divers need specialized pressurized suits or submersibles to protect them from being crushed.
Wow. Even something simple like bubbles rising in water.
Yeah, you can see the effect there too. A gas bubble released at the bottom starts small. As it rises, the external water pressure decreases because H is getting smaller.
So the bubble expands as it goes up.
Exactly, because the internal gas pressure overcomes the decreasing external water pressure. Simple physics in action.
These principles really do explain a lot. Okay, so liquids exert pressure, and it increases with depth. What about transmitting that pressure? I think that leads us to Pascal's law.
It does indeed. Blaise Pascal, brilliant scientist. His principle is fundamental to hydraulics.
So what does Pascal's law state, in essence?
It states that if you apply pressure to any point in a confined, incompressible fluid like a liquid, that pressure increase is transmitted equally and without diminishing to every part of the fluid into the walls of the container.
Equally and undiminished. That sounds powerful.
It is. It's the basis for force multiplication in hydraulic systems.
Is there a simple way to visualize this, like an experiment?
You can imagine a spherical flask filled with liquid, completely sealed, but with several narrow tubes sticking out from it in different directions, and maybe one opening fitted with a piston you can push.
Okay, got it. A spiky ball full of water with a plunger.
Sort of. If you push the piston in, applying pressure at that one point.
The liquid level will rise in all the narrow tubes equally.
Exactly. It demonstrates that the pressure you applied is transmitted uniformly throughout the liquid, pushing it up each tube by the same amount, regardless of the tube's orientation.
That's the core idea behind hydraulic machines then, like hydraulic presses, jacks, brakes.
Precisely. They all exploit this principle. The key is the relationship pressure, force area.
How does that allow force multiplication?
Imagine you have two connected cylinders, one with a small piston, area AA, and one with a large piston, area A. They're filled with hydraulic fluid.
Okay.
If you apply a small force, AO to the small piston, you create a pressure P, ace over aero.
Right.
Pascal's law says this pressure P is transmitted identically to the larger piston.
So the pressure on the larger piston is also P.
Yes, but the force experienced by the larger piston, F aero, will be P times its area, aero. So F aero is PA aero.
Ah, so if P F euro and P equal F euro, then aero must equal F aero.
Exactly. F aero. Rearranging that, you get F euro.
Meaning the ratio of the forces is equal to the ratio of the areas. If the second piston's area is much larger, the output force is much larger.
That's the force multiplier effect.
Yeah.
You put in a small force on the small piston, and you get a large force out from the large piston.
Let's look at a specific example. The hydraulic press, sometimes called a Brahma press. How's that built?
Typically, you have the two cylinders we just described, a narrow one, the pump cylinder, P, and a much wider one, the press cylinder, Q. They're connected by a pipe.
With pistons in each. Let's call them A and B.
Right. Piston A in the pump, piston B in the press cylinder usually have some valves, maybe V and V, to control the fluid flow, and often a lever attached to the pump piston A to make applying the input force easier.
And how does it work?
You apply force, often via the lever, to the small pump piston A. This increases the pressure in the fluid. That pressure travels through the connecting pipe R to the underside of the large press piston B.
And because B has a much larger area than A.
The upward force on B is magnified significantly, enough to press cotton bales, squeeze oil from seeds, extract juice, even shape metal.
Incredible leverage, essentially, using fluid pressure. What about a hydraulic jack, the kind you use for lifting a car?
Same principle, different application. Again, you typically have a small pump cylinder, P, and a larger lifting cylinder, Q, connected by a tube with a valve, V.
And a lever for the pump.
Usually, yes. Piston A is in the pump, piston B is in the lifting cylinder, and supports the platform the load sits on,
So you punt the lever.
which pushes piston A down, increasing pressure in the fluid. This pressure forces fluid through the valve V into the larger cylinder Q, pushing piston B and the load upwards.
And the valve stops it coming back down.
Right, it acts like a one-way street for the fluid, allowing you to lift the load incrementally with each pump strike.
Very useful. Okay, final application. Hydraulic brakes in cars. Critical safety system.
Absolutely critical. And again, Pascal's law is key.
How are they set up?
You have a master cylinder, P, connected directly to the brake pedal via a piston A. This cylinder and connecting pipelines are filled with brake fluid.
And the pipelines go to each wheel.
They go to wheel cylinders on each wheel. Inside these wheel cylinders are smaller pistons, maybe B, I, and B, connected to the brake shoes or pads.
So when you step on the brake pedal,
You push piston A in the master cylinder, creating pressure in the brake fluid. Pascal's law ensures this pressure is transmitted equally and undiminished through the pipelines to all the wheel cylinders simultaneously.
and the pressure in the wheel cylinders pushes their pistons outwards.
Exactly. Those pistons, BA and BO, push the brake shoes against the inside of the brake drum or the brake pads against the brake disc.
Creating friction, slowing the wheel. And there's force multiplication here, too.
Yes, usually the combined area of the pistons in the wheel cylinders is significantly larger than the area of the master cylinder piston A, so the force applied to the brake shoes pads is magnified compared to the force you apply with your foot.
So for all these hydraulic machines, press, jack, brakes, we trade distance for force, right? The small piston moves a lot, the big piston moves a little, but exerts a huge force.
Precisely. Effort is less than the load, but the distance moved by the effort is greater than the distance moved by the load. Ideally, work input equals work output, ignoring friction.
Fascinating applications. Okay, let's shift focus now, upwards, to the air around us, atmospheric pressure.
Right. We live at the bottom of an ocean of air, the atmosphere. It extends, well, maybe 300 kilometers up, though it gets incredibly thin.
And all that air has weight.
It certainly does. And the force exerted by the weight of the column of air above any given area on the Earth's surface, that's atmospheric pressure. Thrust per unit area, just like before.
And it's surprisingly large, isn't it? At sea level, something like...
Around 100,000 newtons per square meter, or 105 pascals. That's like having a weight of 10 tons pressing on every square meter.
Which always leads to the question, if there's that much force pressing on us, why don't we feel crushed?
It's because we have pressure inside our bodies, too. The fluids in our body, our blood pressure primarily, exert an outward pressure that, under normal circumstances, pretty much balances the inward atmospheric pressure.
So it's an equilibrium. We're adapted to it.
Exactly. We only really notice changes or imbalances like when pressure changes rapidly with altitude.
There's a classic experiment that really shows the power of this pressure, the collapsing can.
Ah, yes, a great demonstration. You take an empty metal can, put a little water in it, and heat it until the water boils and steam fills the can, driving out most of the air.
Okay, so it's full of steam, then you seal it tight.
Seal it, then quickly cool it down, maybe by pouring cold water over it.
What happens to the steam inside?
The steam condenses rapidly back into a tiny amount of liquid water. This creates a very low pressure area, almost a vacuum, inside the sealed can.
But the atmospheric pressure outside is still pushing with that huge force.
And with nothing much pushing back from the inside, the external pressure crushes the can quite dramatically.
A very visual proof of that invisible force. And we see its effects in everyday things too, right? Like using a straw.
Definitely. When you suck on a straw, you're not actually pulling the liquid up. You're reducing the air pressure inside the straw.
Ah, so the higher atmospheric pressure on the surface of the drink outside the straw then pushes the liquid up into the low pressure zone.
Precisely. It's all about pressure differences.
Yeah.
Same thing with filling a syringe.
You pull the plunger back, creating low pressure.
And the atmospheric pressure pushes the liquid in. Filling an old-style fountain pen worked similarly.
What about those rubber suckers, like the ones used to hang things on windows?
Same idea. You press the sucker flat against the surface, forcing the air out from underneath. This creates a partial vacuum.
And the atmospheric pressure outside holds it firmly in place.
Until enough air leaks back in to equalize the pressure. Even a siphon system relies on it.
How does that work again? Transferring liquid between containers.
You need to fill the siphon tube completely first. Then, atmospheric pressure pushes down on the liquid in the higher container. This pressure helps push the liquid up the shorter arm of the siphon. Gravity then pulls the liquid down the longer arm into the lower container, maintaining the flow as long as the outlet is lower than the inlet surface.
And even getting oil out of a sealed can, sometimes you need two holes.
Yes. If you only make one hole to pour from, the liquid coming out lowers the pressure inside. Atmospheric pressure outside resists the flow. Making a second hole allows air to enter, equalizing the pressure and letting the oil pour smoothly.
So many examples once you start looking. Okay, how do we actually measure this atmospheric pressure accurately? We need an instrument.
We do. And that instrument is called a barometer.
The original concept came from Torricelli, right? Back in the 17th century.
That's right, Evangelista Torricelli. His simple mercury barometer was revolutionary.
How did he build it? What was the setup?
He took a strong glass tube, about a meter long, sealed at one end. He filled it completely with mercury, which is very dense.
Okay, a tube full of mercury. Then
he carefully placed his finger over the open end, inverted the tube, and submerged the open end into a trough or dish, also containing mercury.
And when he removed his finger,
some of the mercury flowed out of the tube into the dish, but not all of it. A column of mercury remained standing inside the tube, supported by the atmospheric pressure pushing down on the surface of the mercury in the dish.
And the space above the mercury in the tube was empty.
Essentially, yes. A vacuum, or very near vacuum, now known as the Torricellian vacuum. The height of the mercury column that remained in the tube, measured vertically from the surface in the dish, was a direct measure of the atmospheric pressure.
And at sea level, standard pressure, that height is typically
about 76 centimeters or 760 millimeters of mercury, which is also equivalent to 760 torr.
And the height only changes if the atmospheric pressure changes. The width of the tube doesn't matter.
Correct. Doesn't matter if the tube is wide or narrow, or even if it's tilted, it's the vertical height that corresponds to the pressure. Though tilting it makes the column longer along the tube, the vertical height stays the same.
But if some air got trapped in that vacuum space?
Ah, yes. If there's air, or even significant mercury vapor in the Torricellian vacuum, it will exert its own downward pressure, pushing the mercury column down and giving a falsely low reading, a faulty barometer.
Why mercury, though? Why not just use water?
Well, mercury has several advantages. Its high density is key. It means the column needed to balance atmospheric pressure is only 76 centimeters high. Water is much less dense.
How tall would a water barometer need to be?
You'd need a tube over 10 meters tall, about 34 feet. Highly impractical.
Okay, point taken. Any other reasons for mercury?
Yes, it has very low vapor pressure at room temperature, so the vacuum is quite good. It doesn't wet or stick to glass, making readings cleaner. It's shiny and opaque, easy to see, and you can get it in pure state relatively easily.
And water's disadvantages, besides the height?
Well, it has a much higher vapor pressure, which would significantly affect the reading. It sticks to glass, making the meniscus hard to read accurately, and it's transparent. So mercury wins hands down for a simple barometer.
But Torricelli's simple barometer had drawbacks too, right? For practical use.
It did. The mercury surface in the dish was open to dust and contamination. There was no protection for the fragile glass tube. It wasn't portable at all. And reading the height accurately without a proper fixed scale was difficult.
Which led to improvements like the Fortin barometer, often used in labs.
Exactly. The Fortin barometer is a refined version. The glass tube is housed inside a protective brass case. The open mercury reservoir at the bottom is different too.
Oh, so?
It's usually a leather cup or cistern, and there's a screw underneath. Turning this screw adjusts the level of the mercury in the cistern precisely.
Why do you need to adjust it?
Because there's a fixed ivory pointer inside the cistern, pointing downwards. Its tip marks the 0 point of the measurement scale. Before taking a reading, you use the screw to adjust the mercury level until its surface just touches the tip of the ivory point.
Ah, so you always start measuring from the exact same 0 level. Clever.
Very clever. Then you look up at the mercury column through a slit in the brass case. There's a main scale attached, usually in millimeters, and a sliding vernier scale for getting very precise readings, often to 1/10 of a millimeter.
And usually a thermometer attached too?
Yes, because the density of mercury changes slightly with temperature, so you need to record the temperature to make corrections for a standard reading if necessary.
So much more robust and precise than the simple barometer, but still uses mercury, still not exactly pocket-sized.
True. Which brings us to the aneroid barometer. Aneroid, meaning without liquid.
How does that work? No mercury, no liquid at all.
No liquid. Its heart is a small, flexible metal box, usually circular, with corrugated sides to make it springy. Most of the air has been pumped out of this box, so it's partially evacuated.
Okay, a sealed, partly squashed metal can.
Pretty much. The flexible top surface, the diaphragm, moves in or out slightly as the external atmospheric pressure changes.
It bulges out a bit if pressure drops and gets pushed in if pressure rises.
Exactly. And this tiny movement is cleverly amplified by a system of levers and springs connected to a pointer.
And the pointer moves across a dial.
A dial that's been calibrated usually against a mercury barometer to read directly in units of pressure millibars or inches of mercury, or sometimes pascals.
What are the advantages here? Seems quite different.
Big advantages. No liquid, so no spills, no toxicity concerns. It's compact and light, making it portable. It gives a direct reading, no need for adjustments like the Fortin. Much more convenient for many uses.
Like weather forecasting, perhaps. Or carrying up a mountain.
Definitely. Its portability and direct reading make it ideal for those. Which leads us naturally to how atmospheric pressure changes, particularly with altitude.
Right. We know intuitively if you go up a mountain, the air gets thinner. Pressure drops. Why exactly?
Two main reasons. First, fairly obviously, as you go higher, there's simply less air stacked up above you. The height of the air column pressing down is reduced.
Makes sense. Less weight pushing down.
Second, the density of the air itself decreases as you go up. Air is compressible, so gravity pulls most of it closer to the surface. It gets less dense with altitude.
Is that decrease linear? Like drop 1 millibar every 10 meters?
No, not linear at all. Because the density changes too, the pressure drops off more rapidly at lower altitudes and then more slowly higher up where the air is already thin.
So the pressure change is quite significant even for moderately high mountains.
Oh, yes. At the summit of Mount Everest, for example, which is about 8,848 meters, the atmospheric pressure is only around 30% of what it is at sea level. A huge difference.
And this lower pressure has real effects on people, doesn't it?
It certainly does. The most immediate is difficulty breathing. It's not that there's less percentage of oxygen, but the lower overall pressure means the partial pressure of oxygen is lower, making it harder for our lungs to absorb it.
Altitude sickness.
Right. Another common effect is nosebleeds. Because your internal blood pressure remains relatively constant, while the external air pressure drops, the pressure difference across delicate blood vessels, like those in the nose, can cause them to rupture.
Ouch. Anything else? You mentioned fountain pens earlier.
Yeah, that's a classic one. If you fill a fountain pen at sea level, the air trapped in the ink reservoir is at that higher pressure. Go up to altitude, the lower external pressure allows the higher internal pressure to push the ink out, causing leaks.
So pressure changes with altitude, but it also changes at ground level, right? And that relates to weather.
Absolutely. Changes in atmospheric pressure at a fixed location are closely linked to weather patterns. Pressure changes are often driven by changes in air temperature and humidity, which affect the air's density.
So rising pressure usually means one thing, falling pressure another. How do meteorologists use barometer readings?
They watch the trend very closely. For instance, a sudden sharp fall in barometric pressure often indicates an approaching low-pressure system, which could mean a storm or strong winds are coming.
Okay, bad weather likely. What about a slow fall?
A gradual fall usually suggests increasing moisture in the air, maybe leading to rain or overcast conditions.
And if the pressure starts rising,
A gradual, steady rise typically points towards improving weather, decreasing moisture, drier conditions, clearer skies. A high-pressure system moving in.
what if it rises really quickly?
A sudden rapid rise might indicate that dry, possibly cooler air is moving in quickly, often behind a departing storm system. It could mean very dry weather is imminent.
And if the barometer doesn't change much,
Then the current weather conditions are likely to persist for a while. Stable pressure usually means stable weather.
so it's a really useful forecasting tool just by watching those rises and falls.
One of the fundamental tools, yes.
Now, we mentioned aneroid barometers being portable and useful for altitude. That brings us to altimeters in aircraft.
Right. An altimeter is essentially just an aneroid barometer, but its dial isn't marked in units of pressure.
It's marked in units of height, feet, or meters.
Exactly. It uses the predictable relationship between pressure and altitude. As the aircraft climbs, atmospheric pressure decreases,
The aneroid mechanism responds, moves the pointer.
and the pointer indicates the corresponding altitude on the calibrated scale. Because pressure decreases as you go higher, the altitude scale increases in the direction of lower pressure readings, usually counterclockwise on the dial.
So pilots rely on that pressure reading to know their height above sea level based on a standard atmospheric model.
Correct, though they often need to adjust it based on the actual atmospheric pressure at sea level reported by ground stations for accuracy.
Okay, wow. We've covered a lot of ground, or maybe a lot of pressure levels.
Indeed. Quite a journey.
Let's just quickly recap. We started with the basics. Thrust is a force, pressure is force per area, saw how area affects pressure.
Right. Then moved into fluids, liquids, and gases, exerting pressure in all directions, increasing with depth, described by P. Eccles-Haig.
We looked at the laws of liquid pressure and some consequences like dams needing thick bases and why divers need protection.
Then the crucial principle of Pascal's law, transmitting pressure equally in confined fluids.
Which is the magic behind hydraulic systems like presses, jacks, and brakes, allowing force multiplication.
Then we went up into the atmosphere, understanding atmospheric pressure as the weight of air, why we don't feel it normally, but how we can demonstrate it.
And how we measure it, using Torricelli's simple mercury barometer, the more refined Fortin barometer, and the convenient aneroid barometer.
We discussed how pressure decreases with altitude and the effects that has.
And finally, how barometers, especially aneroid ones, are used in weather forecasting by tracking pressure changes, and as altimeters in aircraft by relating pressure to height.
It really is remarkable how these interconnected concepts explain so much, from the mundane, like drinking from a straw, to the critical, like stopping a car or navigating an airplane.
It absolutely is. It definitely makes you think differently about the invisible forces shaping our experience every day. Maybe consider where else these pressure principles might be subtly at play in technology or even nature.
Or think about the challenges and incredible adaptations needed for life to exist under the crushing pressures of the deep ocean or the thin air at extreme altitudes.
Definitely food for thought. This has been a fantastic deep dive. Thanks for joining us.